All right, let's get right into it. Today, we're taking a deep dive into a really key concept in physics, how a capacitor, this deceptively simple little device, manages to store and then unleash energy.
So here's our game plan. We'll start with a real-world example you've definitely seen. Then, we'll get into the nitty-gritty physics of how work gets turned into stored energy. We'll actually derive the formula using a graph, put it through its paces with some examples, tackle a few exam-style questions, and then wrap up with a really fascinating energy puzzle.
First things first, let's connect this idea to something you already know.
I mean, you've seen it, right? A tiny little battery, and then bam, this incredibly bright flash of light. How does that work? Well, the secret isn't the battery alone. It's a capacitor. The battery slowly, patiently charges up the capacitor, and then the capacitor dumps all of that stored energy in one brilliant instant burst. That's exactly the kind of power we're talking about today.
Okay, so how does that energy actually get packed into the capacitor to begin with? It all comes down to a single fundamental idea: work.
You got to think about it like this. A power supply, like a battery, has to literally push charge onto the capacitor's plates, and it's fighting against an electric field that's pushing back. That effort, that physical work that the battery does, it doesn't just disappear into thin air. It gets converted and stored as electric potential energy, just waiting for the right moment to be released.
And here's the really cool part. We don't have to just trust some abstract equation. We can actually see where the energy formula comes from just by looking at a simple graph.
So check this out. If we plot the voltage across the capacitor against the amount of charge stored on it, what we get is this beautiful, perfect straight line. And that tells us that charge and voltage are directly proportional. But here's the real magic. The energy that's stored in that capacitor, it's simply the area underneath this graph.
So let's break it down. It's actually super simple. Step 1, we know the area under the graph is the energy. Step 2, what shape is that? It's just a triangle. Step 3, we all know the area of a triangle, right? It's 1/2 times the base times the height. And for our graph, the base is just the total charge, Q, and the height is the final voltage, V. So, just like that, we get our fundamental equation: the potential energy stored is 1/2 Q times V. It's that elegant.
But wait, we're not done. Using the master equation for all capacitors, Q equals CV, we can actually create two other incredibly useful versions of this formula. If you swap out Q, you get that the energy is 1/2 CV squared. If you swap out V, you get that it's 1/2 Q squared over C. Think of them like 3 different tools in your toolbox. You just pick the one that's perfect for the variables you actually have.
Okay, that's enough theory. Let's get our hands dirty and see how these formulas actually behave in the wild with a couple of quick examples.
All right, for our first one, take a look at what we're given: capacitance, C, and voltage, V. So which formula should we grab? Yeah, it's got to be the one that uses C and V.
So we'll use E equals 1/2 CV squared. From there, it's just plugging in the numbers. We just have to be careful to convert 280 microfarads into standard units, which is 280 times 10 to the minus 6. We multiply that by 12 squared, run the calculation, and we get our answer, 20 milljoules.
Now for something a little more interesting. In this one, we're not looking for the total energy. We want to find out how much energy was transferred as the capacitor discharged and its voltage dropped.
So, to figure this out, we just need to find the energy it had at 9 volts, then find the energy it had left at 4 volts, and then just subtract one from the other. You can even factor out the 1/2 C part to make the formula look a bit cleaner, like you see here. Plug in the numbers, and we find that the energy transferred was about 0.163 joules.
Now hold on, I have to point this out because this is a classic mistake that trips up so many people. V1 squared minus V2 squared is absolutely not the same thing as V1 minus V2 all squared. In our problem, it's 81 minus 16, not 5 squared. It seems like a tiny detail, but it makes a world of difference. Don't fall into that trap.
You're doing great, so let's level up a bit. Let's see how these same ideas pop up in some more challenging questions you might see on an exam.
Okay, take a look at this one. We're given the energy and the capacitance, but we're being asked to find the charge. Notice anything missing? We don't have the voltage. That's our big clue that this is probably a two-step problem. And it is. First, we take our energy formula, E equals 1/2 CV squared, and we rearrange it to solve for V. Once we've calculated that the voltage is 8.94 volts, we can go to step 2 and use our good old friend Q equals CV to find the charge. A quick calculation, and we get 44.7 millicoulombs.
Here's another one, a typical exam question. This time, we're given the voltage and the energy, and we need to work backwards to find the capacitance. Again, it's all about knowing your formulas and being able to rearrange them.
We start with E equals 1/2 CV squared, do a little bit of algebra to solve for C, which gives us C equals 2E over V squared. From there, it's just plugging in the numbers we were given, and that gives us our final answer of 1.67 millifarads. See? You got this.
Wow, we have covered a lot. But before we finish up, I want to leave you with a really fascinating, kind of weird little puzzle that comes out of everything we've just learned.
So think about this. When a battery charges a capacitor, the total amount of work it does, the energy it supplies, is equal to Q times V. But we just proved, using our graph, that the energy the capacitor actually stores is only 1/2 QV.
Now, that's not a mistake in the math. The battery puts in QV worth of energy, but the capacitor only hangs on to half of it. So where did that other 50% of the energy go? It was lost. It dissipated, mostly as heat, through the resistance in the wires and even inside the battery itself during the charging process. It's a perfect little example of the second law of thermodynamics right there in a simple circuit, and a great reminder that in physics, energy never really disappears. Thanks for exploring this with me.